Right now, as you watch this, the Voyager 1 spacecraft is racing through interstellar space at 17 kilometers per second, carrying a golden record with sounds of Earth into the cosmic void. It's the farthest human-made object from our planet, yet after 47 years of travel, it has barely taken the first step outside our solar system's front door. This raises a profound question that keeps me awake at night. Will humanity ever truly leave our cosmic neighborhood and venture to the stars? If you're fascinated by humanity's cosmic destiny and want to explore more mind-blowing questions about our future among the stars, make sure to subscribe to this channel and give a thumbs up. Now let's begin our journey. To understand whether we'll ever leave our solar system, we first need to grasp the absolutely staggering distances involved. Our solar system, defined by the Sun's gravitational influence, extends far beyond the orbit of Neptune. The Kuiper Belt, home to Pluto and countless icy bodies, stretches from 30 to 50 astronomical units from the Sun. But that's just the beginning. The real boundary lies at the Oort cloud, a spherical shell of trillions of comets extending perhaps 2 light-years from our star. Think about that for a moment. Light, the fastest thing in the universe, takes 2 entire years to reach the edge of our solar system. The Voyager probes, traveling at speeds that would cross the United States in 4 minutes, will need 40,000 years to reach the Oort cloud's outer edge. This isn't just far, it's a distance that challenges human comprehension. The nearest star system, Proxima Centauri, lies 4.24 light-years away. If our solar system were the size of a dinner plate, Proxima Centauri would be another dinner plate about 4 miles away. And between these plates, nothing but the vast emptiness of interstellar space, with occasional dust particles and stray atoms. It's like trying to travel from New York to Los Angeles by crawling, except the distance is multiplied by billions. Recent discoveries have made this journey even more tantalizing. In 2016, astronomers discovered Proxima Centauri b, an Earth-sized planet in the habitable zone of our nearest stellar neighbor. The James Webb Space Telescope and ground-based observatories continue to reveal potentially habitable worlds around nearby stars. TRAPPIST-1, just 39 light-years away, hosts 7 Earth-sized planets. These discoveries transform interstellar travel from abstract concept to concrete destination. We now have actual places to go. But knowing where to go and getting there are vastly different challenges. Our fastest spacecraft, NASA's Parker Solar Probe, reaches speeds of nearly 200 kilometers per second when falling toward the Sun. Even at this blistering pace, a journey to Proxima Centauri would take over 6,000 years. Chemical rockets, the technology that took us to the Moon, are fundamentally inadequate for interstellar distances. We need something revolutionary. Enter Breakthrough Starshot, perhaps the most ambitious project in human history. Announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, this initiative aims to send a tiny spacecraft to Proxima Centauri within this century. The plan involves ultralight probes, each weighing just grams, propelled by powerful laser beams to 20% the speed of light. At this velocity, the journey would take about 20 years, with another 4 years for signals to return to Earth. The physics behind Starshot is sound, but the engineering challenges are staggering. The laser array would need to generate 100 gigawatts of power, equivalent to 100 large power plants, focused with extraordinary precision on sails just meters across. The probes must survive acceleration of thousands of Gs, navigate interstellar space autonomously, and transmit data across light years. It's like trying to hit a moving dime with a laser pointer from 1,000 miles away, except the dime is accelerating to 60,000 kilometers per second. Yet Starshot represents just one approach to interstellar travel. Nuclear pulse propulsion, studied in the 1950s and 60s under Project Orion, could theoretically achieve 3 to 5% light speed. This concept involves detonating nuclear bombs behind a spacecraft, riding the shockwaves like a cosmic surfboard. The physics works. We could build this with 1960s technology, but the Partial Test Ban Treaty and obvious safety concerns shelved the project. Modern fusion rockets offer a cleaner alternative. Projects like the British Interplanetary Society's Daedalus study envision unmanned probes powered by fusion reactions, capable of reaching 12% light speed. The Icarus Interstellar project updated these concepts with 21st century technology. These designs could deliver substantial payloads to nearby stars within 50 years of launch, fast enough that the generation that launches them might live to see the data returned, but perhaps we're thinking too conventionally. The Bussard Ramjet, proposed in 1960, would collect interstellar hydrogen as fuel, potentially achieving speeds near light speed. Like a cosmic jet engine, it would grow more powerful as it accelerates, limited only by relativistic effects. The challenge lies in the collection system. The RAM scoop would need to be thousands of kilometers across, built from materials we can't yet manufacture. Solar sails offer another path to the stars. The Japanese Icaros mission and the Planetary Society's light sail projects have demonstrated that photon pressure can propel spacecraft. Scale this technology up, perhaps using laser propulsion like Starshot, and journey times shrink dramatically. The advantage is simplicity: no fuel, no complex engines, just the momentum of light itself pushing gossamer sails across the void. The most speculative propulsion concepts venture into the realm of exotic physics. Alcubierre drives would warp space-time itself, contracting space ahead of a vessel and expanding it behind, potentially enabling faster-than-light travel without violating relativity. The energy requirements are astronomical, originally calculated as the mass energy of Jupiter, though recent refinements have reduced this to merely tons of exotic matter with negative energy density which may not even exist. Wormholes, if they exist and can be stabilized, might offer shortcuts through space-time. The physics allows for such structures, but they would likely collapse instantly without exotic matter to prop them open. Even if we could create and maintain a wormhole, it might lead anywhere in the universe, or nowhere useful at all. It's like having a door that might open to your destination or to the cosmic equivalent of the bottom of the ocean. The human challenges of interstellar travel might prove even more daunting than the physics. Consider the timescales involved. Even with breakthrough propulsion achieving 10% light speed, a journey to Proxima Centauri takes over 40 years. The crew that launches would likely die before arrival. Their children, born in the void between stars, would know Earth only through stories and recordings. This isn't exploration as we understand it. It's voluntary exile from everything that makes us human. Recent psychological studies on isolated populations provide sobering insights. Researchers studying Antarctic bases, submarine crews, and the Mars 500 simulation found that humans struggle with confinement even for months. Depression, conflict, and cognitive decline emerge predictably. Now imagine not months, but decades, not with Earth visible through a window, but with only the cold stars for company. The psychological toll could doom a mission before any technical failure. Yet history shows humans adapting to extraordinary circumstances. Polynesian navigators crossed thousands of miles of open ocean in outrigger canoes, guided by stars and wave patterns. Generation ships, vast vessels where crews live, die, and raise children during centuries-long journeys, might tap into this same adventurous spirit. The key is creating not just a spacecraft, but a living world, complete with ecosystems, culture, and purpose beyond mere survival. The Biosphere. Two experiments in Arizona revealed how difficult creating self-sustaining environments can be. Despite its massive scale and Earth-based advantages, the facility struggled with atmospheric composition, food production, and social dynamics. In space, with no possibility of outside help, every failure could be catastrophic. We need closed-loop life support systems that function flawlessly for centuries, recycling every atom of water, air, and waste with near-perfect efficiency. Genetic engineering might help future interstellar travelers adapt to their journey. Enhanced radiation resistance, reduced metabolic requirements, or even hibernation capabilities could make decades in space more survivable. The ethical implications are staggering. Would these modified humans still be Homo sapiens? Would Earth-born humans and their space-adapted descendants remain the same species after centuries of separation? The recent success of CRISPR gene editing and synthetic biology suggests these aren't idle fantasies. Scientists have already created organisms that thrive in extreme conditions, from radiation-resistant bacteria to tardigrades that survive the vacuum of space. Applied to humans, such modifications could create explorers capable of journeys impossible for unmodified humans. We might engineer not just our spacecraft, but ourselves for the stars. Artificial intelligence could fundamentally change interstellar travel. Instead of sending humans on dangerous decades-long journeys, we might dispatch AI-controlled probes capable of making decisions light-years from Earth. Upon arrival, these probes could construct infrastructure, terraform planets, or even create humans from stored genetic material. It's a strange vision, empty ships carrying the seeds of humanity to distant worlds, with AI gardeners preparing new Edens. The recent advances in AI, from large language models to autonomous vehicles, hint at this possibility. An AI that can navigate city streets might, with development, navigate interstellar space. One that can hold conversations might serve as custodian for a cargo of frozen embryos. The question becomes not whether we can build such systems, but whether we should trust humanity's future to artificial minds. Economic considerations shape every aspect of interstellar travel. The Apollo program, which put 12 humans on the Moon for a total of 300 hours, cost about $300 billion in today's dollars. An interstellar mission would dwarf this expense. Who pays? What return on investment justifies such costs? Unless we discover something revolutionary, exotic physics, alien signals, or existential threats to Earth, funding remains a fundamental barrier. Yet private space companies are changing this calculus. SpaceX has reduced launch costs by orders of magnitude through reusability. Blue Origin, Virgin Galactic, and dozens of startups are creating a space economy. Perhaps interstellar missions won't be government programs, but corporate ventures funded by asteroid mining, space tourism, or technologies we haven't imagined. The first star might be reached not by NASA or ESA, but by some future equivalent of the Dutch East India Company. The detection of interstellar objects passing through our solar system adds urgency to these discussions. Oumuamua in 2017 and Comet Borisov in 2019 proved that material routinely travels between star systems. If rocks can make the journey, why not spacecraft? These visitors also raise tantalizing possibilities. Could some interstellar objects be artificial, derelict probes from other civilizations? The search for extraterrestrial intelligence continues scanning the skies, so far finding only silence. This great silence might mean we're alone, or that interstellar travel is so difficult that civilizations remain isolated. But it might also mean that advanced civilizations have moved beyond radio communications, or that they're already here, unrecognized. Each possibility profoundly impacts humanity's interstellar future. Recent discoveries about extremophiles, organisms thriving in conditions once thought lethal, expand possibilities for life and human adaptation. Bacteria flourish in nuclear reactor cores, in acid mines, in the deepest ocean trenches. Tardigrades survive extreme radiation, temperature, and pressure. Life is more versatile than we imagined. Perhaps humans, augmented by technology and biology, could be equally adaptable. The concept of panspermia, life spreading between worlds, gains credibility with each discovery. If microbes can survive interstellar journeys inside meteorites, perhaps life naturally spreads throughout the galaxy. We might not be pioneers, but participants in an ancient process, with Earth life destined to seed other worlds. Our technology would simply accelerate what nature does slowly. Time dilation, predicted by Einstein and confirmed by countless experiments, offers intriguing possibilities. At speeds approaching light, time passes more slowly for travelers than for those left behind. A journey to a star 10 light-years away might take 12 years ship time, but decades would pass on Earth. Push closer to light speed, and the effect magnifies. Travelers could cross the galaxy in a human lifetime while millennia pass at home. This relativistic trick comes with heartbreaking consequences. Leave Earth at near light speed, and everyone you know ages and dies while you're gone. Return from a journey to find centuries have passed, civilizations have risen and fallen, and the world you knew exists only in history books. It's not just physical distance that separates interstellar travelers from home, but temporal exile that can never be undone. The energy requirements for interstellar travel reveal the true magnitude of our challenge. To accelerate a 1,000-ton spacecraft to 10% light speed requires energy equivalent to humanity's total power consumption for multiple years. Even with perfect efficiency, impossible according to thermodynamics, the numbers are staggering. This isn't just an engineering problem, it's a fundamental constraint imposed by physics itself. Yet recent developments in energy technology offer hope. Fusion power, perpetually 20 years away for decades, has finally achieved net energy gain at the National Ignition Facility in 2022. Private fusion companies like Commonwealth Fusion Systems and Helion Energy promise commercial reactors within a decade. Fusion rockets could provide the specific impulse needed for interstellar missions, turning the hydrogen between stars from obstacles into fuel. Antimatter represents the ultimate rocket fuel. When matter and antimatter annihilate, they convert entirely to energy, the maximum possible by Einstein's famous equation. A few kilograms of antimatter could propel a spacecraft to significant fractions of light speed. The problem? We currently produce antimatter in quantities measured in individual atoms at costs of trillions of dollars per gram. Unless we discover natural antimatter sources or revolutionize production, this remains science fiction. The interstellar medium itself poses unique challenges. Space between stars isn't empty but filled with hydrogen atoms, dust grains, and cosmic rays. At high speeds, these become deadly projectiles. A dust grain hitting a spacecraft at 10% light speed carries the kinetic energy of a bullet. Hydrogen atoms become radiation, requiring massive shielding. The faster we go, the more dangerous space becomes, a cosmic catch-22. Recent data from the Voyager probes, now in interstellar space, provides our first direct measurements of this environment. The magnetic fields are stronger than expected, the cosmic ray flux higher, the plasma density variable. These findings inform future mission designs but also reveal new challenges. Interstellar space is not the calm void we imagined, but a turbulent medium with its own weather patterns. Navigation presents another profound challenge. At interstellar distances, even tiny errors compound into massive deviations. A 1-degree error at launch means missing your target star by light years. GPS doesn't work between stars. Pulsars, rapidly spinning neutron stars emitting regular radio pulses, might serve as cosmic lighthouses, but identifying and tracking them from a moving spacecraft requires capabilities we're still developing. The Parker Solar Probe and Solar Orbiter missions demonstrate our growing ability to operate in extreme environments. Parker has touched the Sun's corona, surviving temperatures exceeding 1,000,000 degrees. These technologies, heat shields, autonomous navigation, radiation-hardened electronics, are stepping stones to interstellar capability. Each mission teaches us something essential about surviving far from Earth's protective embrace. Communication across interstellar distances challenges our concept of conversation. A radio signal to Proxima Centauri takes 4.24 years each way. A simple exchange, hello, hello back, spans nearly a decade. For more distant destinations, entire human lifetimes pass between call and response. This isn't communication as we understand it, but archaeological messaging, where replies arrive for our descendants. Breakthrough. Listen, the most comprehensive SETI project ever undertaken, uses the world's most powerful radio telescopes to scan millions of stars for artificial signals. The technology developed for this search, advanced signal processing, interference mitigation, pattern recognition, would be essential for maintaining contact with interstellar missions. We're learning to whisper and listen across cosmic distances. The material science requirements for interstellar travel push beyond current capabilities. We need substances that remain stable for centuries, self-healing materials that repair micrometeorite damage, and structures that withstand both the near absolute zero of space and the searing heat of stellar approach. Graphene, carbon nanotubes, and metamaterials hint at possibilities, but scaling from laboratory samples to spacecraft hulls remains an enormous challenge. Recent advances in additive manufacturing 3D printing might enable self-repairing spacecraft. Imagine a vessel that can fabricate replacement parts during flight, recycling damaged components into new ones. The entire spacecraft becomes a living system, adapting and evolving during its journey. This biomimetic approach could solve the maintenance challenges that doom conventional designs over century-long missions. The discovery of rogue planets, worlds ejected from their star systems to wander interstellar space, adds an intriguing possibility. These dark worlds might serve as stepping stones between stars, offering resources and gravitational assists. Some might even harbor subsurface oceans warmed by radioactive decay, providing oases of life in the cosmic desert. Our path to the stars might not be empty void, but dotted with islands. Astrobiology influences every aspect of mission planning. The discovery of potentially habitable exoplanets raises profound questions. Do we have the right to colonize worlds that might harbor indigenous life? How do we prevent contamination in either direction? The Outer Space Treaty provides some framework, but interstellar distances make enforcement impossible. We must police ourselves in the cosmic frontier. Speaking of cosmic mysteries and the origins of everything we see, this connects to fundamental questions about our universe itself. If you're curious about alternative theories to our cosmic beginning, check out my video called "What If the Big Bang Never Happened?", where we explore mind-bending possibilities about the nature of existence itself. The link is in the description below and pinned on the comments. The role of private organizations in interstellar planning grows yearly. The Tau Zero Foundation, Icarus Interstellar, and the Initiative for Interstellar Studies bring together scientists, engineers, and visionaries to solve these challenges. Unlike government programs constrained by election cycles, these groups think in centuries. They're designing not just spacecraft, but the cultural and organizational structures needed for multi-generational projects. Recent developments in quantum technology might revolutionize spacecraft systems. Quantum sensors could detect gravitational waves, dark matter, or navigation hazards invisible to conventional instruments. Quantum computers might solve the trajectory optimization problems that classical computers find intractable. Quantum communication, while not faster than light, offers unhackable security for mission-critical systems. The concept of seed ships presents an alternative to sending full-grown humans. These vessels would carry genetic material, artificial wombs, and AI caretakers to raise the first generation on arrival. It's a strange vision, children raised by machines on alien worlds, knowing Earth only through databases. Yet it sidesteps many challenges of generation ships while raising profound ethical questions about consent and human identity. The timeline for interstellar travel stretches human planning beyond any historical precedent. Cathedral builders in medieval Europe committed to projects spanning centuries, but they could see daily progress, pass skills to apprentices, and worship in partially completed structures. Interstellar missions require maintaining focus, funding, and purpose across dozens of generations with no tangible returns. It's like asking someone to plant a forest they'll never see for descendants they'll never meet. Recent studies of long-term thinking reveal how poorly humans plan beyond decades. Climate change, despite clear science and dire consequences, struggles for adequate response. Nuclear waste storage, requiring security for 10,000 years, pushes the limits of our institutional memory. Yet, interstellar travel demands planning for hundreds or thousands of years. We must evolve psychologically and culturally to think in deep time. The Svalbard Global Seed Vault demonstrates one approach to long-term preservation. Buried in Arctic permafrost, it safeguards agricultural heritage against catastrophe. Similar thinking could preserve the knowledge, culture, and genetic diversity needed for interstellar colonization. Multiple redundant archives, some on Earth, others in space, perhaps some already en route to the stars, ensuring humanity's legacy survives even if Earth doesn't. Closed ecological systems remain one of the greatest challenges. The International Space Station requires constant resupply from Earth, about 7,000 kilograms of water annually, plus food, oxygen, and replacement parts. A generation ship must recycle everything with near-perfect efficiency for centuries. Recent experiments with bioregenerative life support show promise, but also reveal unexpected complications, like the buildup of trace contaminants that no filter can remove. The Melissa project by the European Space Agency attempts to create a closed-loop life support system using bacteria, algae, plants, and chemical processes. Early results show 70 to 80% efficiency in recycling water and oxygen. Pushing this to the 99.9% required for interstellar travel remains a monumental challenge. Every lost atom is irreplaceable between the stars. Cultural preservation during interstellar journeys presents unique challenges. Language evolves rapidly. English from just 600 years ago is barely comprehensible today. Over centuries of interstellar travel, ship languages might diverge so far from Earth languages that communication becomes impossible. Digital archives help, but they require maintenance, translation, and cultural context that might be lost as generations pass. The selection of interstellar colonists raises profound ethical questions. Who chooses who goes? What genetic diversity is required? Should we select for intelligence, physical health, psychological stability, or genetic compatibility? History's examples of eugenics warn against such selection, yet the constraints of interstellar travel demand difficult choices. We must balance genetic diversity with mission requirements while respecting human dignity and choice. Recent advances in hibernation research offer potential solutions. Scientists have successfully induced torpor in mammals that don't naturally hibernate, reducing metabolic rates by 90%. Extended to humans, this could transform decade-long journeys into subjective weeks. The challenges remain enormous, preventing muscle atrophy, bone loss, and cellular damage during years of suspension, but the potential benefits drive continued research. The discovery of extremophiles in Earth's most hostile environments expands our concept of habitable zones. Organisms thriving in nuclear reactors, acid lakes, and deep rock formations suggest life is more adaptable than we imagined. Perhaps humans, augmented by genetic engineering and nanotechnology, could adapt to conditions on exoplanets we currently consider uninhabitable. The definition of Earth-like might be unnecessarily restrictive. Robotic precursor missions could prepare the way for human arrival. Swarms of small probes could survey target systems, identify resources, even begin terraforming or constructing habitats. By the time humans arrive, centuries later, infrastructure would await them. This approach separates the risky exploration phase from human colonization, though it requires extraordinary faith that the robot's work will succeed. The von Neumann probe concept takes this further. Self-replicating spacecraft could spread throughout the galaxy, exploring every star system within millions of years. Each probe would use local resources to build copies of itself, creating an exponentially growing exploration network. The fact that we see no evidence of such probes raises disturbing questions about the fate of technological civilizations. Recent observations of Tabby's star, with its irregular dimming patterns, sparked speculation about alien megastructures. While natural explanations proved correct, the episode demonstrated our readiness to detect artificial modifications of stars. Future telescopes might identify Dyson spheres, stellar engines, or other artifacts of advanced civilizations. Discovering such structures would fundamentally change our approach to interstellar travel. The ethical implications of terraforming extend beyond simple environmentalism. Even apparently lifeless worlds might harbor subsurface microbes or represent unique geological laboratories. Do we have the right to transform entire planets for human habitation? The answer impacts not just mission planning, but our fundamental relationship with the cosmos. Are we gardeners entitled to cultivate the universe, or visitors obligated to minimize our impact? Power generation during interstellar flight presents unique challenges. Solar panels become useless far from any star. Nuclear reactors require fuel that adds mass and maintenance complexity. Proposed solutions include fusion ramjets that collect interstellar hydrogen, antimatter catalyze propulsion, or even dark matter interactions. Each solution pushes the boundaries of physics and engineering. The possibility of uploading human consciousness to digital form offers a radical alternative. If minds can exist in silicon as well as carbon, interstellar travel becomes far simpler. No life support, no radiation shielding, no generational planning, just protected computer cores housing thousands or millions of digital minds. The philosophical questions are staggering. Would uploaded beings still be human? Would digital existence be worth achieving? Recent advances in brain-computer interfaces by companies like Neuralink hint at this possibility. While current technology merely reads and stimulates neural activity, the trajectory points toward deeper integration. Combined with advances in artificial intelligence and quantum computing, consciousness uploading might transition from science fiction to engineering challenge within this century. The sociological dynamics of interstellar colonies would be unlike anything in human history. Imagine a generation ship with 10,000 people, isolated for centuries between stars. Traditional governments, designed for millions across continents, wouldn't work. These ships would need new forms of organization, perhaps AI-assisted democracy, rotating councils, or structures we haven't imagined. The wrong political system could doom a mission as surely as engine failure. Historical analogies offer limited guidance. The mutiny on the Bounty after just 2 years at sea shows how quickly isolated groups can fracture. The lost colony of Roanoke vanished entirely. Even successful colonies like Australia required constant resupply and communication with their home nations. Interstellar colonies would be truly alone, forced to solve every crisis with only onboard resources and knowledge. Recent experiments with distributed decision-making and blockchain governance suggest possibilities. Decentralized autonomous organizations operate without traditional hierarchies, using smart contracts and consensus mechanisms. Applied to interstellar missions, such systems might prevent the concentration of power that historically leads to tyranny or rebellion. Every colonist could have a voice, every decision transparent, every resource allocation borne. The reproductive challenges of interstellar travel remain largely unexplored. We don't know if humans can conceive in zero gravity or reduced gravity. Radiation exposure might cause genetic damage passed to offspring. The minimum viable population for genetic diversity is debated. Estimates range from hundreds to tens of thousands. Too few colonists risk inbreeding. Too many strain life support systems. Research on the International Space Station reveals concerning effects. Sperm counts decrease, hormone levels shift, and cellular damage accumulates. Female astronauts face additional challenges with changed menstrual cycles and potential pregnancy complications. These short-term effects hint at profound, long-term consequences for reproduction between stars. We might need artificial wombs or genetic engineering to maintain healthy populations. The role of artificial intelligence in interstellar missions continues evolving. Current AI can diagnose diseases, pilot spacecraft, and even create art. Future AI might serve as teachers, therapists, and companions for isolated colonists. But dependence on AI raises questions. What if it fails? What if it evolves beyond human control? The HL scenario from 2001, A Space Odyssey, reflects real concerns about autonomous systems making life or death decisions light years from Earth. Recent breakthroughs in artificial general intelligence suggest these aren't distant concerns. Language models demonstrate reasoning, creativity, and even apparent emotion. As capabilities grow, the line between tool and teammate blurs. Interstellar missions might include AI crew members with rights and responsibilities equal to humans. The first interstellar colony might be a hybrid civilization of biological and artificial minds. Resource extraction from asteroids and comets could sustain interstellar missions. The asteroid Psyche contains enough iron to supply humanity for millions of years. Other asteroids hold platinum, rare earth elements, and water ice. A generation ship could stop at resource-rich systems along its path, refueling and restocking like ancient sailing ships at ports. This island-hopping approach to interstellar travel makes the journey more feasible, but much longer. The Japanese Hayabusa missions, which returned samples from asteroids, prove we can rendezvous with and extract resources from these bodies. Scaled up dramatically, similar technology could turn asteroids into fuel depots and supply caches for interstellar missions. The challenge lies in processing raw materials in space, smelting metal, purifying water, synthesizing complex chemicals, all without Earth's industrial infrastructure. Cultural and linguistic evolution during interstellar journeys would create profound changes. After centuries of isolation, ship populations would develop unique dialects, customs, and worldviews. Children born between stars might struggle to understand Earth literature, music, or values. By arrival, colonists might be culturally alien to the civilization that launched them. We're not just sending humans to the stars, but creating new branches of humanity. Studies of isolated populations on Earth provide glimpses of this evolution. The Piraha people of the Amazon developed a language without numbers, colors, or creation myths. Iceland's population, isolated for centuries, evolved unique genetic markers. Interstellar populations would experience far more extreme isolation, potentially becoming distinct subspecies of humanity given enough time. The discovery of biosignatures in exoplanet atmospheres would revolutionize mission planning. The James Webb Space Telescope can detect oxygen, methane, and other potential signs of life in distant atmospheres. Finding a genuinely Earth-like world with existing life would create enormous pressure to visit, study, and possibly colonize. But it also raises the stakes. Contamination in either direction could be catastrophic. Recent analysis of Venus's atmosphere revealed phosphine, a potential biosignature, though this remains controversial. Similar discoveries around exoplanets would face even greater uncertainty. We might launch centuries-long missions toward worlds that only might harbor life, gambling entire civilizations on spectroscopic hints. The cost of being wrong in either direction is almost unimaginable. The possibility of encountering alien civilizations, however remote, shapes every aspect of interstellar planning. Do we announce our presence or stay hidden? Do we assume benevolence or prepare defenses? The dark forest hypothesis suggests that civilizations stay quiet to avoid destruction by more advanced species. Our interstellar missions might need to balance exploration with stealth, seeking new worlds while avoiding detection. SETI continues scanning for signals, while Amiti, messaging extraterrestrial intelligence, actively broadcasts to nearby stars. These efforts assume aliens use radio, but advanced civilizations might communicate through gravitational waves, neutrinos, or methods we haven't discovered. Our interstellar probes might stumble upon alien artifacts or active civilizations without recognizing them. The economic motivation for interstellar colonization remains unclear. Unlike European colonization driven by gold, spices, and territory, interstellar colonies offer no economic return for centuries. Some suggest existential risk mitigation, ensuring humanity survives Earth-ending catastrophes. Others see manifest destiny, spreading life throughout the cosmos. But these philosophical motivations might not sustain the enormous costs across generations. The propulsion breakthroughs needed for practical interstellar travel might come from unexpected directions. Recent experiments with electromagnetic drives, though controversial, hint at possibilities beyond conventional physics. The Mach effect thruster, based on fluctuations in mass caused by acceleration, could theoretically provide propellantless propulsion. While current results are disputed, the principle suggests that our understanding of inertia and mass might be incomplete. Quantum vacuum thrusters attempt to push against the quantum foam of space-time itself. By creating asymmetric boundaries in the vacuum, these devices might extract thrust from empty space. The energy densities involved are minuscule, but if scaled up, they could provide continuous acceleration without fuel. It sounds like magic, but so did nuclear power to 19th century physicists. The role of metamaterials in spacecraft design opens extraordinary possibilities. These engineered structures have properties not found in nature: negative refractive indices, acoustic cloaking, and electromagnetic manipulation. Future metamaterials might provide perfect radiation shielding, self-healing hulls, or even manipulation of gravitational fields. We're learning to engineer matter at the atomic level, creating designer materials for specific challenges. Recent developments in nuclear propulsion have renewed interest in this approach. NASA's Draco program aims to demonstrate nuclear thermal propulsion by 2027. Nuclear electric propulsion could provide steady thrust for decades, slowly but continuously accelerating spacecraft to high velocities. While not sufficient alone for interstellar missions, nuclear propulsion is a crucial stepping stone toward more exotic technologies. The preservation of human knowledge during interstellar journeys presents unique challenges. Digital storage degrades over time, bit rot, cosmic ray damage, and hardware failure threaten any electronic archive. Physical books are bulky and deteriorate. DNA storage, encoding information in synthetic genetic sequences, offers incredible density and longevity. A gram of DNA could store all human knowledge, preserved for thousands of years if properly maintained. Microsoft's Project Silica explores storing data in quartz glass using femtosecond lasers. These archives could last millions of years without power or maintenance. An interstellar mission might carry humanity's entire cultural heritage in a few kilograms of engineered glass, ensuring colonists retain connection to their origins even after centuries of travel. The psychological profiles of successful interstellar colonists would differ markedly from typical astronauts. Current space missions are selected for peak performance, assuming eventual return to Earth. Interstellar colonists need different qualities: adaptability over achievement, cooperation over competition, contentment over ambition. We might need to rethink our entire selection process, choosing for psychological sustainability rather than exceptional capability. Research on submarine crews, Antarctic researchers, and isolated communities reveals crucial traits. Emotional stability matters more than intelligence. Social skills outweigh technical expertise. The ability to find meaning in routine and joy in small pleasures becomes essential. These aren't the bold explorers of fiction, but careful gardeners tending humanity's future across the void. The discovery of time crystals, structures that repeat in time rather than space, hints at new physics that might revolutionize interstellar travel. These quantum systems exhibit perpetual motion without violating thermodynamics, maintaining coherence indefinitely. While current time crystals exist only at microscopic scales, the principle might scale to macroscopic applications, perhaps enabling perpetual motion machines or exotic propulsion systems. Recent experiments have created time crystals in diamond using microwave pulses, demonstrating room temperature stability. If we can engineer time crystal-based systems, they might provide perfect timekeeping for navigation, quantum computers that never decohere, or even manipulation of time itself. The implications for interstellar travel are purely speculative, but profoundly intriguing. The manufacturing capabilities required for self-sufficient colonies push beyond current technology. 3D printing offers a starting point, but colonists need to produce everything from microchips to medicines. Molecular assemblers, building objects atom by atom, represent the ultimate manufacturing technology. With raw elements and energy, such devices could create any material or device, making colonies truly independent. Current additive manufacturing can print metals, ceramics, and biological tissues, but not the complex integration required for advanced technology. Colonists might regress technologically, unable to replace sophisticated equipment. This technological decay could strand colonies at pre-industrial levels, defeating the purpose of interstellar expansion. Maintaining technological civilization requires capabilities we're only beginning to develop. The astrobiology implications of interstellar colonization grow more complex with each discovery. Extremophiles on Earth survive conditions once thought impossible. Tardigrades endure the vacuum of space. Bacteria thrive in nuclear reactors. If Earth life is this resilient, alien life might be everywhere, in forms we don't recognize. Our colonies might always be invasive species disrupting ecosystems we don't even perceive. The precautionary principle suggests extreme caution, but perfect sterility is impossible. A single human carries trillions of microorganisms. Our colonies will inevitably introduce Earth life to other worlds. The question becomes not whether we'll contaminate, but how we'll manage the inevitable biological exchange. Perhaps spreading life is not contamination, but destiny, the universe becoming aware of itself through biology's expansion. Recent observations of interstellar asteroids like Oumuamua reveal that objects routinely travel between star systems. Over millions of years, significant material exchange occurs naturally. Panspermia, life spreading between worlds, might be common. Our interstellar missions might not introduce life to sterile worlds, but add Earth's branch to an already interconnected cosmic ecosystem. The communications infrastructure for interstellar civilization would dwarf anything humans have built. Maintaining contact with colonies around multiple stars requires transmitters powerful enough to span light years, receivers sensitive enough to detect whispers across the void. The Deep Space Network, which maintains contact with Voyager at merely 23 billion kilometers, hints at the scale required. Laser communication offers higher bandwidth than radio, with successful demonstrations between Earth and lunar orbit. Scaled up, laser arrays could maintain high-bandwidth connections between stars. But this requires precise pointing across light years, massive power generation, and infrastructure that must operate for centuries without maintenance. Each colony becomes an island connected to humanity by the thinnest thread of light. The legal framework for interstellar colonization remains embryonic. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but it was written when interstellar travel was pure fiction. Who owns a planet colonized by a generation ship launched by a defunct corporation from a nation that no longer exists? These aren't hypothetical questions, but real challenges that will shape humanity's expansion into the cosmos. Recent developments in space law, driven by companies like SpaceX and Blue Origin, are creating precedents. The Artemis Accords attempt to establish principles for lunar mining and Mars colonization. But enforcing laws across light years is impossible. Interstellar colonies will inevitably develop their own legal systems, potentially diverging radically from Earth norms. We might be seeding the cosmos not with one human civilization, but many, each with its own concept of justice, property, and rights. The energy requirements for maintaining technological civilization on other worlds are staggering. Earth's biosphere provides free services, oxygen production, water cycling, waste processing, that require enormous energy to replicate artificially. A Mars colony might need nuclear reactors just to maintain breathable air. An interstellar colony without even a distant sun for power faces even greater challenges. Energy poverty could doom colonies to subsistence existence. Fusion power offers hope using hydrogen, the universe's most abundant element, as fuel. The ITER project in France and private ventures like TAE Technologies are approaching commercial fusion. For interstellar colonies, fusion isn't just helpful, but essential. Without it, technological civilization might be impossible beyond Earth. The ability to build and maintain fusion reactors might determine which colonies thrive and which regress to pre-industrial subsistence. The medical challenges of interstellar colonization extend beyond radiation and bone loss. Closed populations face unique epidemiological risks. A single pathogen could devastate a generation ship with no possibility of outside help. Conversely, lack of pathogen exposure might leave colonists vulnerable to even mild diseases. The immune systems of colonists might atrophy or evolve in unexpected directions, making return to Earth biologically impossible. Recent advances in synthetic biology offer solutions. Scientists have created artificial antibodies, programmed bacteria to fight cancer, and engineered viruses to deliver gene therapy. Future colonists might carry biological factories capable of producing any medicine from raw materials. Disease itself might be engineered away, with colonists' immune systems upgraded to handle any threat. But this requires capabilities we're only beginning to develop. The role of virtual reality in maintaining sanity during interstellar journeys cannot be overstated. Confined to a ship for decades, colonists need psychological escape. Advanced VR could provide entire worlds to explore, social connections with Earth-based humans, and experiences impossible in reality. The line between real and virtual might blur, with some colonists choosing to live primarily in digital worlds while their bodies travel between stars. Current VR technology already enables presence, the feeling of being elsewhere. Haptic feedback, neural interfaces, and full-body tracking continue improving. Within decades, VR might be indistinguishable from reality. For interstellar travelers, this isn't entertainment but psychological necessity. The ability to walk through forests, swim in oceans, and feel sunshine might preserve sanity across the void. The discovery of potential technosignatures, signs of alien technology, would fundamentally change our approach to interstellar travel. If Voyagian stars dimming proved artificial, if fast radio bursts carried messages, if we detected megastructures or stellar engines, everything changes. We'd know interstellar civilization is possible, that others have solved the challenges we face, but we'd also know we're not alone, with all the opportunities and dangers that implies. The search continues with ever more sophisticated instruments. The Square Kilometre Array will survey millions of stars simultaneously. The Laser Interferometer Space Antenna will detect gravitational waves from across the universe. Machine learning algorithms sift through data, searching for patterns human minds might miss. Any day could bring the discovery that transforms interstellar travel from human adventure to cosmic imperative. The terraforming technologies required to make other worlds habitable push the boundaries of planetary engineering. Mars needs a thicker atmosphere, higher temperature, and magnetic field. Venus needs cooling, atmospheric processing, and rotation adjustment. Even seemingly simple changes like adding oxygen to an atmosphere require moving gigatons of material and enormous energy. We're talking about re-engineering entire worlds, playing God on a planetary scale. Recent proposals include solar shades to cool Venus, orbital mirrors to warm Mars, and artificial magnetospheres to protect atmospheres. Some suggest bombarding Mars with comets to add water and thicken the atmosphere. Others propose genetically engineered organisms to transform atmospheric chemistry. These aren't near-term possibilities, but multi-century projects requiring sustained commitment across generations. The philosophical implications of interstellar colonization challenge our deepest beliefs. If we spread across the galaxy, are we still one species or many? Do colonies have obligations to Earth or each other? Should we preserve human nature or embrace radical enhancement? These questions don't have clear answers, but our responses will shape the future of intelligence in the universe. Consider the ship of Theseus paradox applied to humanity. After centuries of isolation, genetic drift, and cultural evolution, are interstellar colonists still human? If we replace our biology with machinery, upload our minds to computers, or merge with artificial intelligence, what remains of humanity? We might preserve the form while losing the essence, or transform the form while preserving what truly matters. The role of religion and spirituality in interstellar missions deserves consideration. Confined populations under stress often turn to faith for comfort and meaning. But whose faith? How do diverse beliefs coexist in confined spaces? Some suggest creating new mythologies suited to life between stars, providing meaning without Earth's baggage. Others argue that preserving Earth's religious diversity is essential to maintaining human identity. Recent studies of astronaut spirituality reveal profound changes. Many report overview effect experiences. Seeing Earth from space triggers feelings of unity and transcendence. Imagine the interstellar effect of seeing our sun as merely another star. Such experiences might birth new philosophies or religions unique to those who venture beyond Earth's embrace. We're not just exploring space, but the boundaries of human consciousness. The timeline for developing interstellar capability stretches across multiple technological revolutions. Consider that just 66 years separated the Wright brothers' first flight from Apollo 11 landing on the Moon. If we maintain similar exponential progress, the seemingly impossible becomes achievable. By 2100, technologies we can't imagine today might make an interstellar travel routine. But this assumes continuous advancement without civilizational collapse, a big assumption given climate change, nuclear weapons, and other existential risks. Recent analyses of technological development reveal interesting patterns. Major breakthroughs often require the confluence of multiple technologies. The Internet needed computers, telecommunications, and protocols developed independently. Similarly, interstellar travel might await convergence of fusion power, artificial intelligence, nanotechnology, and discoveries we haven't yet made. We might be closer than we think, or crucial pieces might remain missing for centuries. The role of megastructures in enabling interstellar civilization deserves exploration. Orbital rings around Earth could launch spacecraft without rockets. Shkadov thrusters could move entire stars, bringing destinations to us rather than traveling to them. Matryoshka brains could provide computational power to simulate billions of human minds, making physical travel unnecessary. These structures require engineering on scales that dwarf current capabilities, but might be achievable given centuries of development. The breakthrough propulsion physics program, though terminated in 2002, explored exotic concepts like warp drives, traversable wormholes, and faster-than-light communication. While no breakthroughs emerged, the research established frameworks for evaluating speculative physics. Private efforts continue this work, seeking loopholes in Einstein's speed limit. A single discovery could transform interstellar travel from millennia-long ordeals to practical journeys. Recent experiments with quantum teleportation have achieved remarkable successes. Chinese scientists teleported photons from Earth to satellite, demonstrating quantum information transfer across thousands of kilometers. While this doesn't enable faster-than-light communication or transportation of matter, it shows that quantum mechanics still holds surprises. Perhaps future discoveries will reveal ways to exploit quantum phenomena for interstellar travel. The biological modifications necessary for thriving on other worlds go beyond simple adaptation. We might engineer humans who photosynthesize, reducing food requirements. Colonists could hibernate for decades, awakening only when needed. Radiation resistance could be built into our DNA. These aren't minor tweaks, but fundamental redesigns of human biology. The question becomes, how much can we change and still remain human? CRISPR and other gene editing tools make such modifications increasingly feasible. Scientists have already created genetically modified babies, though the ethical backlash was severe. For interstellar colonization, such modifications might be not just acceptable, but necessary. The colonists who reach other stars might be as different from us as we are from our earliest ancestors, adapted for environments we can barely imagine. The data storage requirements for preserving human knowledge are staggering. Every book, song, scientific paper, and cultural artifact, the complete record of human civilization, must be preserved and accessible. Current estimates suggest humanity generates several zettabytes of data annually. Storing this for centuries, protecting it from radiation and decay, and ensuring future colonists can access it requires revolutionary approaches to information preservation. DNA storage offers incredible density, all human knowledge in a shoebox, but reading and writing remains slow. Quantum storage could preserve information in atomic states, potentially lasting millions of years. Crystal lattices can encode data in 3 dimensions, accessed by laser. Each approach has advantages, and interstellar missions might use multiple methods for redundancy. Losing humanity's accumulated knowledge would be a tragedy beyond measure. The economic models for funding interstellar missions challenge traditional thinking. No corporation expects returns on thousand-year investments. No government plans beyond election cycles. Yet the costs are so enormous that only large-scale collective efforts could succeed. New economic structures, perhaps based on cryptocurrency, automation, or post-scarcity abundance, might be necessary. Some propose gradual approaches where each generation builds on previous work. Others suggest crash programs triggered by existential threats. The discovery of an approaching asteroid, solar instability, or hostile aliens could motivate unprecedented investment. Alternatively, if automation eliminates human labor, society might redirect vast resources toward interstellar expansion as a new purpose for civilization. The discovery of extremophiles in Antarctica's subglacial lakes provides insights for astrobiology. Lake Vostok, isolated for millions of years beneath kilometers of ice, harbors unique microorganisms. These creatures thrive without sunlight, in near-freezing water, under crushing pressure. If life exists in such extreme Earth environments, similar conditions on Europa, Enceladus, or exoplanets might also harbor life. Recent missions to Jupiter and Saturn's moons reveal subsurface oceans containing more water than Earth. The Europa Clipper mission, launching in 2024, will search for biosignatures. Discovery of even microbial life would revolutionize our understanding of life's prevalence. If life is common, interstellar colonization becomes about joining a living universe rather than spreading life to dead worlds. The cultural preservation challenges during interstellar journeys extend beyond language and customs. Music, art, cuisine, sports, all aspects of human culture must be maintained or consciously abandoned. A generation ship needs not just life support, but theaters, galleries, sports facilities. Virtual reality might preserve experiences impossible in space, surfing, mountain climbing, seasons changing. But some argue physical culture must be maintained. Studies of cultural transmission show that practices requiring specific environments disappear quickly when those environments change. Seafaring skills vanished when populations moved inland. Traditional crafts die when materials become unavailable. Interstellar colonists might maintain Earth culture through careful curation or develop entirely new cultural forms suited to life between stars. The radiation environment of interstellar space poses challenges beyond simple shielding. Galactic cosmic rays include particles with energies millions of times higher than anything we can create. These particles shower secondary radiation when they hit shielding, potentially making thick shields worse than thin ones. Active shielding using magnetic or electric fields might work, but requires enormous power. We might need to accept radiation exposure as inevitable, engineering biology to repair or tolerate damage. The search for Earth-like exoplanets has revealed an unexpected diversity of worlds. Super-Earths, mini-Neptunes, hot Jupiters, and rogue planets challenge our assumptions about planetary formation. The Kepler mission discovered that most stars host planets, but true Earth analogues remain rare. TRAPPIST-1's 7 terrestrial planets orbit so closely that you could see neighboring worlds as large as our Moon from their surfaces. These alien configurations might require completely different colonization strategies than we've imagined. Recent observations by the James Webb Space Telescope have detected atmospheres around rocky exoplanets, analyzing their composition with unprecedented precision. K2-18b shows signs of water vapor and possibly even biological signatures. LHS 1140b might have a thick atmosphere despite orbiting a red dwarf. Each discovery refines our target list for interstellar missions, but also reveals how little we understand about planetary habitability. The concept of generation ships assumes multiple generations living and dying during the journey, but recent sociological research questions this model's viability. Studies of isolated communities show that knowledge and skills erode within just 3 generations without external input. Critical expertise, medical, engineering, agricultural, might vanish as children choose different paths than their parents. A generation ship needs not just genetic diversity but professional diversity maintained across centuries. Alternative models include sleeper ships, where most colonists remain in suspended animation tended by small rotating crews. This reduces resource consumption and social dynamics challenges, but requires perfect reliability of hibernation systems for centuries. A single failure could doom thousands. The psychological burden on awake crew members, knowing they'll die in space while others reach the destination, might prove unbearable. The discovery of metallic hydrogen in laboratory conditions hints at exotic materials that could revolutionize spacecraft design. This phase of hydrogen, theorized to exist in Jupiter's core, could be a room-temperature superconductor and the most powerful rocket fuel possible. If we could manufacture and stabilize metallic hydrogen, it might provide both the structural materials and propulsion needed for interstellar travel. Recent experiments at Harvard using diamond anvil cells created metallic hydrogen at 495 gigapascals of pressure. While the sample was lost before complete verification, the achievement suggests this exotic matter is within reach. Scaling from microscopic samples to industrial production remains an enormous challenge, but the potential rewards justify continued research. The preservation of genetic diversity during interstellar colonization requires careful planning. Small populations face inevitable inbreeding unless genetic material is preserved and strategically introduced. Frozen embryos, sperm, and egg banks could maintain diversity, but these require reliable cryogenic storage for centuries. Artificial wombs might gestate genetically diverse offspring, but the technology remains primitive. Recent advances in reproductive technology offer possibilities. Scientists have created functional egg and sperm cells from skin cells, potentially allowing same-sex reproduction and genetic rescue of endangered species. Extended to interstellar colonization, this technology could maintain genetic diversity with smaller populations. Each colonist could contribute to hundreds of genetic combinations without traditional reproduction. The navigation challenges for interstellar missions compound over time. Stars move relative to each other. Proxima Centauri won't be in the same position when a slow mission arrives. Precise trajectory planning requires predicting stellar positions centuries in advance, accounting for gravitational perturbations we might not yet know about. A navigation error of 1 part in a billion could mean missing the target system entirely. Pulsar navigation offers a solution. These rapidly spinning neutron stars emit regular radio pulses, creating natural beacons visible across the galaxy. By triangulating signals from multiple pulsars, spacecraft could determine their position to within kilometers, even light-years from Earth. NASA's Sextant experiment on the ISS demonstrated pulsar navigation feasibility. Future missions might navigate between stars using these cosmic lighthouses. The question of consciousness and identity during interstellar travel raises profound philosophical issues. If we upload minds to computers or use teleportation-style transportation that destroys and reconstructs travelers, are they the same person? Does consciousness survive suspended animation? These aren't merely philosophical puzzles, but practical concerns that might determine how we approach interstellar colonization. Recent neuroscience research reveals that consciousness might be more robust than we thought. Patients recovered from long-term comas report continuous experience despite apparent unconsciousness. Studies of split-brain patients show consciousness can divide and merge. These findings suggest human consciousness might survive transitions we currently consider impossible: uploading, downloading, or distribution across multiple platforms. The environmental ethics of terraforming other worlds presents difficult choices. Even apparently barren planets might host subsurface microbes or represent unique geological laboratories. do we have the right to transform entire worlds for human habitation? Some argue that spreading life is a moral imperative, others that we should minimize our cosmic footprint. These philosophical differences might split interstellar colonization efforts into competing factions. The discovery of life, even microbial, would complicate these ethics enormously. We might find that life is rare and precious, deserving protection at all costs, or we might discover that life is ubiquitous and resilient, making our careful contamination protocols unnecessary. Until we explore other worlds, we're making ethical decisions based on profound ignorance about life's cosmic prevalence. The possibility of machine intelligence surpassing human intelligence before we achieve interstellar travel changes everything. Artificial general intelligence might solve the technical challenges that stump human engineers. It might also decide that biological humans are unsuitable for interstellar colonization, choosing to spread machine intelligence instead. We might achieve interstellar travel only to find we're passengers, not pilots. Recent advances in artificial intelligence, from large language models to autonomous systems, suggest AGI might arrive within decades. These systems already exceed human capabilities in specific domains. When they achieve general intelligence, they might solve interstellar travel challenges in ways we never imagined, or decide that physical travel is unnecessary, choosing instead to transmit intelligence as information at light speed. As we stand at this cosmic crossroads contemplating humanity's interstellar future, we must confront a profound truth. The journey to the stars will transform us as much as we transform the worlds we reach. We won't be the same species that left Earth when we arrive at distant suns. Evolution, biological, cultural, and technological, will reshape us in ways we can barely imagine. The humans who finally walk beneath alien stars might look back at us as we look at our earliest ancestors, recognizing kinship but marveling at the distance traveled. The window for interstellar expansion might be narrower than we assume. Earth's resources are finite, and our technological civilization depends on elements that took billions of years to concentrate into accessible deposits. If we exhaust these resources before achieving interstellar capability, we might trap ourselves on Earth permanently. This isn't pessimism but urgency. We have perhaps centuries, not millennia, to develop the technologies needed for interstellar travel. Recent climate modeling shows how fragile our technological civilization is. Rising temperatures, resource depletion, and ecological collapse could end our spacefaring dreams before they truly begin. Some argue that surviving climate change is practice for terraforming. If we can't maintain Earth's habitability, how can we create it elsewhere? Others see interstellar colonization as insurance against Earth's challenges. Both perspectives emphasize urgency. The discovery of phosphine in Venus's atmosphere, though disputed, reminds us that life might exist in places we never expected. If microbial life survives in Venusian clouds, Martian subsurface, or Europa's oceans, it suggests life is not rare but tenacious. This would transform interstellar colonization from spreading life to dead worlds to joining a living universe. Every world might harbor its own genesis, its own tree of life that we must respect and protect. The most optimistic timeline suggests we might launch our first interstellar probe within this century. Breakthrough. Starshot aims for the 2040s, sending gram-scale probes to Proxima Centauri. These pathfinders would return images and data by mid-century, inspiring further missions. Crewed missions might follow by 2200 using technologies we're just beginning to imagine. It's ambitious but not impossible. More conservative estimates place crewed interstellar missions centuries or millennia in the future. We might need to solve fusion power, create closed ecosystems, develop suspended animation, and overcome countless other challenges. Each breakthrough enables the next, but progress isn't guaranteed. Civilizations can stagnate or regress. Rome had concrete and aqueducts, then lost the knowledge for centuries. We must actively choose progress. The role of private enterprise in achieving interstellar travel grows yearly. SpaceX reduced launch costs by orders of magnitude through reusability. Blue Origin, Virgin Galactic, and dozens of startups are creating a true space economy. Perhaps governments won't lead humanity to the stars. Corporations might, driven by profit motives we haven't yet imagined. Asteroid mining, space manufacturing, or technologies we can't foresee might fund interstellar missions. The discovery of technosignatures, evidence of alien technology, would catalyze interstellar efforts. Knowing that others have achieved interstellar travel would prove it's possible. Competition, curiosity, or fear might drive unprecedented investment. SETI continues searching, and every null result paradoxically increases the importance of spreading Earth life. If we're alone or rare, we bear responsibility for consciousness in the cosmos. The philosophical implications of our interstellar future shape how we see ourselves today. If humanity spreads across the galaxy, creating millions of worlds with billions of inhabitants, then we're living in the most crucial period of human history. Our decisions about technology, environment, and society determine whether Earth remains humanity's only home or becomes the birthplace of a galactic civilization. Consider the perspective of future historians on an interstellar colony, looking back at Earth's 21st century. They might see us as the generation that opened the universe or the one that almost closed it forever. Every choice we make about climate, technology, education, cooperation ripples forward through time. We're not just living our lives, but shaping the trajectory of intelligence in the cosmos. The ultimate question isn't whether we'll leave our solar system, but what we'll become in the process. Will we remain recognizably human, carrying Earth's legacy to distant stars? Will we transform into something unimaginable, adapted for environments we've never experienced? Will we merge with our machines, upload our minds, or discover new forms of existence? The journey to the stars is also a journey into the unknown depths of human potential. As you contemplate these possibilities, remember that you're part of this story. Every person who looks up at the stars and wonders, everyone who studies science or supports space exploration, everyone who dreams of humanity's cosmic future contributes to making it real. We might not live to see interstellar colonies, but we're laying the foundation. The cathedral builders of tomorrow's interstellar civilization are working today. The stars call to us as they've called to every human generation, but we're the first with the knowledge to answer. We know the distances, the challenges, the physics that must be overcome. We have telescopes revealing worlds to explore, rockets reaching beyond Earth, and minds capable of imagining solutions. What we need is the will to try, the wisdom to persist, and the courage to transform ourselves for the journey. Will we ever leave our solar system? The answer depends on choices we're making right now. If we protect our planet, advance our technology, and maintain our curiosity, then yes, humanity will walk beneath alien suns. If we fail, if we turn inward and abandon the stars, then Earth becomes our eternal prison and eventual grave. The universe doesn't care which we choose, but our descendants will live with the consequences forever. Look up at the stars tonight with new eyes. Each point of light is a destination, a possibility, a future waiting to be claimed. The journey will be long, difficult, and transformative. We'll face challenges that seem impossible today, but we are the species that looked at the moon and decided to visit, that decoded DNA and split the atom, that asked impossible questions and found improbable answers. The stars aren't beyond our reach, they're our destiny if we choose to claim it. The greatest adventure in human history hasn't begun yet, but we're writing its prologue. Every breakthrough in physics, every advance in technology, every moment of wonder at the cosmos adds another page. Someday, perhaps sooner than we think, humanity will take its first steps beyond the solar system. When that moment comes, it will be because people like you refused to accept that the stars were forever out of reach. The journey of 1,000 light years begins with a single dream, and that dream lives in all of us who dare to look up and wonder, what if? If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How far does our galaxy actually reach? Discover how recent discoveries from Gaia, Hubble, and Fermi have shattered old ideas about where our galaxy ends, uncovering tidal streams, satellite galaxies, magnetic fields, and much more. See you there.